Hi, and welcome to the polynomial section. So, first and foremost, what are polynomials? Polynomials are expressions that involve one or more variables, which are represented using letters such as x, y, and z, having different powers and different coefficients. So here are some examples. First, a polynomial based on one variable. In this case, the variable is x. Next, a polynomial with two variables. In this case, the variables are x and y. Then, an example with more than two variables. This example has quite a lot of variables. In this case, it would be 6 total, so x, y, z, a, b, and c. I use this example to demonstrate two main points. One is that a polynomial can have many different variables. As earlier mentioned, polynomials are used to model different things, and you can think of each variable as representing one specific aspect. So, depending on how complex you need to make the model, you can have as many variables as necessary. And then, the second thing is, you shouldn't stick to the idea, or you shouldn't keep the idea in your mind, that variables can only be x, y, or z. Technically, they can be any letter you want. They just need to represent some number that you don't know, or some number that can vary. So you can use the usual x, y, or z, or you can use an a, you can use a b, you can use a c, or if you so wish, you could be fancy and use a Greek letter, such as alpha or beta even. But yeah, coming back to the English alphabet, it's useful to be comfortable with this idea that variables don't have to be x or y, they can be anything. So just having this kind of mindset will make you much more comfortable with working and playing around with variables. Then the last two things that are important to note are, firstly, the exponents, meaning this, for example, those have to be natural numbers. And what that means is they need to be greater than or equal to 1. So, for example, you have this expression, so all of these are greater than 1, so this can be considered a polynomial. And then, but in this case, the exponent is 1 over 3, the fraction, meaning it's less than 1. This is a negative 5, meaning it's less than 0, in fact, negative number. Both these terms, they violate that rule, meaning that this cannot be considered a polynomial. So that's the first thing I want to demonstrate, and the last thing is the coefficients of the variables. For example, 0.5 here, this root 2, or then for the other example, here you have 4, you have 2, you have 3. So the coefficients, these can be any real number, meaning they can be positive, negative, fractions, whatever. So I use this example to demonstrate that. So you have 0.5, that sign, that works. You have a root 2 here, works. And for the number at the end, you have a pi, that's also fine. It just needs to be a real number. So anything with a complex number, you wouldn't consider it a polynomial. By that logic, this also works. So to summarize, the main thing you need to keep in mind is, for it to be considered a polynomial, you can have more than one variable, and you can have fraction or irrational numbers as your coefficients for your variables, but you cannot have anything less than 1. Fractions and decimals, for example, or negative numbers. Then another question you may have in your mind is, why even learn about polynomials? That's a good question. These are worth learning about because they can be used to model various everyday things that can be described mathematically. A simple example of this is a shopping list. Say you want to buy some apples and bananas and want to calculate the total price of your shopping list based on how much of each you buy. So you are varying the number of each that you're going to buy. Therefore, you can have your variables as number of apples being A and number of bananas being B. Next, let's say that one apple is 3 Rand and one banana is 5 Rand. So the total amount of money you'd spend, depending on how many apples or bananas you buy, would be T for total equals price of each apple times number of apples plus price per banana times number of bananas. So, using this equation, you could test how buying different amounts of apples and bananas would add up to give you your total shopping bill that day. For example, say you're in a situation where your total budget is 20 Rand. Then you're trying to see how many fruits you can afford in that amount. So then you first consider, okay, I think I like both equally, so maybe I'll get 3 apples, 3 bananas. Then when you use the equation, you find out that 3 of each may not work out. So this would be beyond your budget of 20 Rand. So then you consider, okay, I think I don't like banana as much, so maybe if I just buy 2 bananas instead, it could work. So you check it out again using the equation. So for this combination, you find out that the total would come to 19 Rand and therefore would fit in your budget of 20 Rand. Therefore 3 apples and 2 bananas it is. Yay! So that was a very basic but sort of practical example of how you can use polynomials. But essentially, polynomials are a fundamental way of modeling many things you can encounter in real life and also just theoretically, and are therefore quite useful. As a result, they're used extensively in science and engineering, as well as commerce and economics, to name a few. Now that you know what polynomials are, the next question is, how exactly are we going to use them? In this section, we'll be looking at, firstly, cubic polynomials, then the remainder and factor theorem, and lastly, how to solve cubic equations. Let's begin. Firstly, cubic polynomials. So, a cubic polynomial is an expression with the highest exponent of its variables being equal to 3. Another way to say this is that the degree of the polynomial is 3. The general form of a cubic polynomial is, in this case, the a, b, c, and d don't actually represent variables. Rather, they're the coefficients of the variable being x. And an important thing to note is that a cannot be equal to 0. And that's because if a was 0, then this term would fall away and the polynomial would be of order 2. So you cannot have the x cubed term's coefficient being 0. However, you can have any of these other coefficients being 0. So some valid examples of cubic polynomials would be, these are 3 different examples of cubic polynomials. In the first one here, you have the value of a being 1, the value of b being 0 because there's no x squared term, the value of c being 1 as well, and the value of d also being 1. And in the second example, you have a being 3, and again there's no x squared term. Here you have c being negative 2, and d is plus 1. And then final example, you have a being minus 10, and then in this case you'd have b and c as 0, so no x squared or x term, but d is there as 2. In case you're wondering, you can have the d as 0 as well, so you could have something like, in this case, everything's coefficient except x cubed is 0, and that's fine. It's still considered a cubic polynomial. The main condition is you have to have the one term with the x cubed. Doesn't really matter what its coefficient is as long as it's a real number. But yeah, you have to have the one term with the x cubed, and the others you don't really need to have any of them. The next part of the video is the remainder and factor theorem. The two are quite related, but I'll start off with the remainder theorem. Similarly to how you can multiply 2 expressions to get a resulting expression, for example, you can multiply x minus 2 and x plus 3, which would give you x squared minus 2x plus 3x minus 6, which gives you x squared plus x minus 6. Similarly, you can also divide an expression by another to get another expression. We can apply this to the same example. In this case, let's say you divide this result, x squared plus x plus 6, by x plus 3. This example is quite nice because we already knew x minus 2 is a factor, so we knew it would come out nicely like this. But instead, what about in the case where x squared plus x minus 6 is divided by an expression that isn't a factor? So we can choose anything just to demonstrate the point. For sake of simplicity, I'll just divide it by x plus 1, which would give me, for this example, When you divide x squared plus x minus 6 by x plus 1, you get x with a remainder of minus 6. This is quite similar to the idea of dividing one number by the other. For example, say dividing 10 by 3, you would get 3, so 3 times 3 equals 9, and then the remainder would be 1. So you apply the exact same principle to these expressions. Now, I realize you're probably wondering what just happened over here. So I didn't give an explanation of this whole method of division because it's not really important to know about and you won't need to use it in your final exam or anything. But in case you're interested, there's two ways by which you can do this division. One is this method, which is long division, and the other is called synthetic division. If you're interested in how these work, I'll include a link in the resources. Anyway, with this we come to the remainder theorem, which is simply as follows. To find what remainder you'd get after dividing a polynomial p by the term ax minus b, you can get the remainder by simply substituting the value b over a into the polynomial p to get the remainder r. It may seem a bit fuzzy just seeing all these different terms, but I'll demonstrate this in action using a few examples. In the first example, you have to divide the polynomial 3x cubed plus 5x squared minus x plus 1 by the expression x plus 2. So the first thing to do is determine the value of x that you're going to substitute in here. So you need to keep in mind that you have to have the expression in this form first. So rewriting this expression in that form gives x minus minus 2, which when you compare to the ax minus b form, you get a equals to 1 and b equals to minus 2. Now you can calculate the value of x. When you do this, you get x as negative 2. Then you just substitute it into this equation. 3 times negative 2 cubed, which is negative 8, plus 5 times negative 2 squared, which is 4, minus negative 2, which is plus 2, plus 1, which gives you negative 24 plus 20 plus 2 plus 1, which finally comes to negative 1. And that's the value of the remainder when you divide p by x plus 2. For the next example, what is the remainder when you divide p by 2x minus 1? First, you need to arrange in terms of ax minus b. I'm looking at the expression, it's already in that form, so you can take a and b just straight off. Then you calculate your x as b over a, which gives you half or 0.5. Again, you just substitute this into p, which gives you 17 over 8 or 2.125, and that's the remainder. Then last, a slightly more tricky one. In this case, you're dividing p, which was 3x cubed plus 5x squared plus x plus 1 by x plus m. So like previous, you first need to represent it in the ax minus b form, which gives you x minus negative m. Therefore, a is 1 and b is negative m. Finally, value of x is minus m over 1 or minus m, which again you just substitute into the expression for p. 3 times minus m cubed plus 5 times minus m squared minus m plus 1, which comes down to minus 3m cubed plus 5m squared plus m plus 1. So the answer may seem incomplete because you still have a big whole equation like this, but using all of the information that we've been given, this is what we've ended up at. So that's the final answer. Let's look at a second example. The question states that use remainder theorem to determine the remainder when polynomial h is divided by polynomial y. Polynomials h and I are as follows. So polynomial h is a cubic polynomial similar to the ones we've been looking at so far, and polynomial I is a simple linear polynomial. So the first step, like before, is taking the polynomial you're dividing by, in this case I, and rewriting it in the ax minus b form. When you do that, you get 5x minus minus 1, which by comparison to the ax minus b shown right below it, tells you that a equals to 5 and b equals to minus 1. Then you get the value of x by saying b over a, which in this case is minus 1 over 5, or also minus 0.2. Then it's just the final step where you substitute this value of x into the polynomial h. This is what it looks like, and when you type this into your calculator, you get 11, and that gives you the remainder you're looking for. It's also worth keeping in mind that the remainder theorem doesn't only apply to cubic polynomials, it can actually be used for any polynomial. For example, the polynomial p, which has an x term to the power of 100 and another just to 1. It still qualifies as a polynomial, and you can therefore use the remainder theorem on it. In this example, we want to divide it by q, which is equal to x plus 1. Again, same set of steps as before. So first you represent this in the ax minus b form. From this, you can tell that a is 1 and b is negative 1. Therefore, x is equal to b over a, or negative 1 over 1, which is just negative 1. Then you substitute this into p, and this gives you 2. And that's the remainder. Now that we have a pretty good feel of how to apply the remainder theorem, let's try solidify it in our minds by applying it in a slightly different type of question. The question is, calculate the value of b if, when divided by the polynomial 2x cubed minus 7x squared plus bx minus 26 by x minus 2, you get the remainder of negative 24. The approach for solving this is very similar to how we did before. We go step by step. You have x minus 2, then you want to represent it in the ax minus b form, so that would be, and in this case it doesn't really change much because it's pretty much already in the ax minus b form. For this case, a would be 1 and b would be 2. Therefore, x equals 2 over 1, which is the same as 2. Then you just substitute this value of x into the polynomial. Then when you simplify this, you get, which finally comes down to, the remainder calculated by our usual method is 2b minus 38. Then the question also told us that the remainder is negative 24. To solve for b, all we need to do is equate the two terms. So r equals to r, meaning 2b minus 38 equals to negative 24. And finally, that gives us b equals to 7. I think we've covered enough about the remainder theorem now. Something worth noting is that in the exam, they most likely won't ask you a question where, for example, you need to find the remainder when some expression is divided by another. However, the concept is worth keeping in mind because it's quite fundamental to the next part, which is the factor theorem. And the factor theorem applies more to the type of knowledge you need to know and apply in your exam. We can now look at the factor theorem. The factor theorem builds upon the remainder theorem and looks at a specific case of it. What it states is that if you divide a polynomial p by an expression, so exactly the same way like we've been dividing various polynomials by different expressions and finding the remainder. Like in the example we just looked at, here this was your p and this is the expression you're dividing by. What the factor theorem states is that when you do this division and you find out the remainder, so how we did it before by saying x is equal to b over a, then substituting that value of x into the polynomial, and after doing that we'd get the remainder r. The unique point that the factor theorem makes is that if you find that the remainder has a value of 0, then this means that ax minus b is actually a factor of p. To demonstrate the idea, let's look at some examples. The question states that using the factor theorem, show that the expression x plus 4 is a factor of the polynomial p, which is 5x to the power 4 plus 16x cubed minus 15x squared plus 8x plus 16. The first thing to think about is, how am I going to show that x plus 4 is a factor of p? The question specifies that you need to do this using the factor theorem. And you come back to the factor theorem over here and remember what it says. That if you divide the polynomial p by the term ax minus b, which in this case is x plus 4, which is also the exact same as just substituting the value of x in this expression, or like before, b over a. When you substitute this value of x into the polynomial p, you get the remainder. And if the remainder is 0, then it proves that x plus 4 is a factor. So let's try it out. First, you rewrite this in the form ax minus b, which gives you x minus 4, meaning a equals 2, 1, and b equals 2, and therefore x equals to b over a, which is negative 4 over 1, which is also just negative 4. Now, the final step, substitute the value of x, meaning negative 4, to polynomial p. When you do this, it should look like this becomes, which finally gives, which is, as you can tell, 0. This directly demonstrates the factor theorem in action, where you divided the polynomial p by x plus 4, which is the same as substituting this x value into equation for p, and finally you got 0. And through the factor theorem, this confirms that x plus 4 is indeed a factor of p. We can put a different spin on this by looking at another example. In this second example, the question is 3x minus 3 a factor of the same polynomial p? How do we determine this? By dividing p by 3x minus 3. Like always, we start by representing it in the ax minus b form. So from this we can tell that a is 3 and b is 3 as well. Therefore, x is equal to 3 over 3, which is the same as 1. Then we substitute this into p, like before, giving us, and this equals 30. Meaning, when we divide polynomial p by 3x minus 3, we get a remainder of 30. And since this remainder isn't equal to 0, according to the factor theorem, 3x minus 3 isn't a factor of p. If you feel you're comfortable with all the material we've covered so far under polynomials, so this mainly being what cubic polynomials are, the remainder theorem, and the factor theorem, let's see how this connects to the type of questions you'd get in an exam. From all of this, the main idea that you need to keep in mind is that for any expression ax minus b, when you solve for x using b over a and substitute this value of x into a polynomial containing various x terms, such as, for example, p, which we looked at before, if you get a value of 0, that means that the expression ax minus b is a factor of p. It's this pretty simple conclusion which we arrived at by looking at all those things we did, such as just general polynomials, remainder, and factor theorem. This basic conclusion, you can use it to solve cubic polynomials to find out their various factors. Let us see how this is used. For the first example, we need to factorize the polynomial m. So the first thing that you do to factorize the equation is you use the factor theorem to determine one factor through trial and error. What this means is that basically choose random values of s, substitute them into this polynomial m, and you keep doing this till you get a result of 0. That's the same as getting a remainder of 0, and that implies that you've now found a factor. And this can be the first factor of the equation. So while the concept is you try random numbers and see if they work, you try random numbers in a structured way. So you start off small. So you first start off with a nice simple number such as 1. Then you substitute this into polynomial m, like that, which gives you, and that is 0. So how lucky we are. The very first value of s we tried gave us a remainder of 0. Therefore that confirms that s equals to 1 is a factor. And when you rearrange this by taking the 1 to that side, you get s minus 1. Now that you have your first factor, you want to find the other leftover factors. How many factors are there in total? 3. And that's because you have an s cubed over here, meaning that the polynomial is of the order 3. Therefore, 3 factors. You found your first factor, you want to find your other 2 factor. The way you do this is by a method called inspection. The first thing you need to do is rewrite this in a different form, which includes this s minus 1. When you do that, you get, so you rewrite your polynomial m. So m is equal to blah 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 is equal to, now you're writing it down in the factorized form. So you have your first factor s minus 1, which you already determined, and that'll be times some term in brackets which you still need to determine. This is where the method of inspection comes in. The method works by comparing what you have on one side to what you have on the other side. So the first bit is you think, what can I multiply s by to get s cubed? So you think of it as s times some unknown term equals s cubed. Then you can just rearrange it to solve for the term in the brackets. So the term in the brackets equals to s cubed over s, which is s squared. And now you have the first term in the second bracket. First you look at the first term in the second bracket, then you look at the last term in the bracket. You think, what number can I multiply negative 1 with to give me 6? And you can write that in a similar form to this term over here. So that is this term times something in brackets equals to this term. Negative 6, which you write at the very end, and you can close the bracket. So now you have the first and the last term in the brackets. All you're missing is the middle term. So the overall equation is a quadratic polynomial, and by that logic you will know that the second term will end with an s. So now you know the overall form of the equation. You're just left with finding the coefficient in front of the s term. To determine the coefficient of the middle term, you use the middle terms in the original cubic polynomial. You can choose either of them. Don't worry, it's not as complicated as it may seem. You basically just need to choose one of them. Your choice. Doesn't matter which one. Say I feel like choosing the s squared term. So I'll determine it by inspecting the ways in which you can get s squared terms by multiplying these two polynomials. We're focusing on s squared, so you say on the left side you have negative 2, then you equate it to the s squared terms that you can get by multiplying this factor with this quadratic polynomial. So you say equals to, the first s squared term you get is by multiplying negative 1 and s squared, which will give you negative s squared. Just in terms of coefficients, that would be negative 1. Then the other way you can get an s squared term is by multiplying this s with whatever its coefficient is by this s. So plus s times coefficient in front of this will give you something s squared. So you can just put it as a bracket here. Then you rearrange and solve for the bracket to get to negative 2 plus 1, negative 1, which you can put in front of the s, which would be negative 1, s would just be negative s. And now you have the quadratic polynomial. That was how you can determine this coefficient using s squared. Now let's look at how you can determine it using the s term. So going back to a situation where we don't know the coefficient for this yet, and we're going to approach it by looking at the s term, the original cubic polynomial. So what we have in this polynomial is negative 5s. Then we equate it to the s terms you can get by multiplying these two bracket terms together. The one way you can get an s term is by multiplying this s with this negative 6, which will give you negative 6s. So the s coefficient is negative 6. Then the other way you can get an s term is by multiplying this negative 1 times whatever coefficient is here and s. When we do that, we get plus negative 1 times empty bracket. Then you rearrange for the bracket and you get negative bracket equals negative 5 plus 6, which is 1. Then you take the negative on the other side, and now you can get the bracket term as negative 1, which is exactly the same answer as when you use the s squared term. Write it in here. One useful thing you can do, using the fact that you'll get the same answer using both s squared and s, is if you use one of them and you get a certain value, but if you want to make sure that your value is correct, you can try doing the same thing with the other term and see what you get. And if you get the same thing, then you know for sure you've got the correct answer. Now let's say that you're about 80% of the way to solving the question. So you have the first factor, and then you have the quadratic polynomial that arises when you multiply the other two factors. Now all you need to do is factorize the quadratic polynomial, and then you'll have the three factors and we'll have answered the question. So in previous grades, you should have learned how to factorize a quadratic polynomial. So I won't go over that again. I'll just give you the answer you get. You get s minus 3 and s plus 2. Putting this all together, you get your three factors as s minus 1, s minus 3, and s plus 2. And with that, you've answered the question. I can imagine it's probably still a bit confusing, so let's look at a few more examples.